Hello, so today we're going to talk about triplanar mapping in Copernicus. And first I'll show you the tool, how it works, and then we'll dive inside and I'll show you how it was built. And of course you can find the link in the description to download it. So the first thing that you want to do when using this triplanar mapping tool, we need pref and rest normal attributes, right? So we have our test geometry and we add the rest node to get the pref and the rest normals. So then I have this megascan textures and I want to apply this to my object. So I have a SOP import with my geometry and a preview material. So if I visualize this, we can see our texture mapped, but we can see some seam line on the UV island where the texture is not repeating, and we can probably mess with the transform to find a better position for it that kind of blends a little bit better, or we can use triplanar projection. So we can simply add our HDA to the scene, which I have one already, plug our geometry in and our texture file in the RGB channel and plug this into the base color. And already you can see we have better transition in between the seam line and other parts, like in front here. And we can change a few settings here. You can translate your geometry. You can rotate on each axis the plane of projection, right? You can scale it on each individual axis or all together to find what works the best. And then we can mirror one of the two axes, in this case the X negative, the Y negative, and the Z negative, to get different result. Sometimes you have this, depending on the geometry, sometimes you might see this mirror points over here, and sometimes you might not, so that's why we have this option. And we can also change our blending in between the two axes. We can have like a very sharp blend or a more smoother blend, and of course this blend can be remapped. And we also have this noise multiplier where we can take 3D noise, add it into our noise slot, and then use this to further distort the projection UV that are generated. And that's pretty much it for the tool. There's only this one last thing with this sample mode, where we can use Rasterize, which is the vanilla Copernicus node for rasterizing attributes from geometry to UVs, or the Wrangle node. And the way there's a switch is because Rasterize, it's a lot faster to work with, almost like half the speed, but then Wrangle solves another issue that I'll show you now. So let's unlock this and dive inside. And basically what we have is our inputs here, geometry, our texture, and the noise. We take the geometry, we use a Rasterize setup to basically flatten it out and put it into UV space. And then we have our Rasterize geo, which basically is, actually, let's lock this over here so we can always see it, and dive back inside. So let's go to this switch. And we have this Rasterize method, which takes the pref and the normal attributes. And you can see it gets rasterized only up until the UVs. After that, we get black. And this might cause some issue further down the line when you manipulate this information. And at the end, you might see black or lines, artifacts around the UV islands, edges, and seam lines. So in order to avoid that, we can switch to this Wrangle node. And shout out to Rohan Dalvi for making a tutorial about this. That basically is just a simple Vex snippet that does the same thing that this node does, a bit slower, but at the same time, if we switch to that, this happens. So basically this node does some padding or diffusion from the edge of your UV island and just fills in everything until it meets with another UV island that is trying to fill. So this way we won't have any black or dark pixel or artifacts on our UV's sim line. And basically the way I figured is like you can use this to visualize, have a quicker preview of what you're doing, and then when you're saving to texture, just switch to wrangle, and you should avoid having problems on the sim line of the UV island. So can keep it for rasterize up to now. So as I said, we rasterize our geometry in this 2 method, and then we have the transform vector that is basically rotating around, translating it and scaling our information. And we have this add node that takes in the noise that we are feeding with a multiplication that is basically our control on the amount of noise that we can add to this information. And as you can see, it's basically just like, it's kind of like taking each pixel and say, oh, move this over here in space. We are just visualizing positional space into in this case. And we can just add on top of it a 3D noise or another texture, anything that you want to further distort this position attributes. Then once we have that, we just split RGB, that basically are our X, Y, and Z component in space. And this seems like a lot, but it's actually the very same thing 6 times over. So X plus, X minus, Y plus, Y minus, and so on. So we take X and Y in this case, and we recombine them together. And this already started to look like a UV map, but instead of being from 0 to 1 in this space, is from 0 to 1 in the position of the object space. From there, in the X minus, we have our mirror switch. So if we go here, we should be able to see the difference, and it does not. Well, anyway, that's what it does. We take this information and we use this now as a UV, just a UV map basically. And we say, I want to take these textures with the sample node and map it using these UVs. And it's going to look very wrong in here, but it's all going to make sense when everything gets blended through. Then once we have this, and let's plug this in directly here, go up 1 level, and we see what happens here. We have basically done a UV mapping projection from this plane onto our object, and everything else just gets distorted away because it's always the same, basically kind of pixel in space that says, oh, map this pixel here, and then just keep doing it because there's no other information, right? So we need to take our normals, and again here we have our rotation control, and we take those normal, we do a dot product with the direction of our axis that we want to look up. In this case is going to be, don't do that, if we go back up, it's this direction, Z plus, right? Take that, we dot product, that gives us this, which we can use as a mask to mask this projection over here. So there's a remap to clamp it, there's a power, that's our exponent, another clamp again, and then we make it from mono to RGB, and we multiply this over our texture. If we plug this in in here, we can now see what's going on. So I want to project, actually, let's do this properly. There we go. We're basically doing this, mapping this from this projection, and then we can control how much of a fall off we want for this single axis projection. And we just do this 6 times over, Xplus, sorry, Zplus, Zminus, and so on. Take this, we blend it with the next projection, we blend it with the next projection axis, and we blend it again with the next projection axis. And now if we connect this, we go back up, we have our projection from all axes with our blending happening. And there you go. And you can now take this and process further or save the textures and do whatever you want. And yeah, that's pretty much it.